Our knowledge of black holes, which are enigmatic space anomalies, is still developing. They are difficult to locate, and even more so to investigate. The space around these fascinating objects undergoes radical alterations, defying the laws of physics as we know them. Hello, and welcome to ZE. Please don't forget to subscribe and hit the bell icon. Investigating black holes can help us learn more about the deeper meaning of our cosmos. However, they also pose a potential risk. How hazardous are black holes then? Firstly, it should go without saying that finding a celestial object that is completely opaque to light is a difficult endeavor. This explains why the current pool of potential black hole candidates is so small. Nevertheless, computational simulations indicate that there might be 100 million of them in our galaxy. Although this may seem like a very large quantity, considering that the Milky Way is home to 200 to 400 billion stars, it helps us to know that black holes are an uncommon object in all of these vast spaces. We noted that a star, which is the parent of a black hole, needs to have a mass of at least 18 to 20 solar masses in one of our earlier movies on the subject. This is the only way to guarantee a strong enough supernova to condense the star's blazing hot core into an incredibly dense mass of matter. Once this occurs, nothing can resist the object's gravitational attraction and depart, leaving behind the Schwarzschild radius-determined borders of a regular sphere. What was once a star is now an odd object whose internal composition defies explanation by known physical rules. One of the black holes that we are aware of that is closest to Earth is the object known as A0620-00, or V616 Mon. It is a member of the Monoceros constellation's binary star system and is located 3,300 light-years from Earth. An orange dwarf, half the mass of the Sun, is the other object in the system. Every 7.75 hours, it completes a full circle around an unseen object of undetermined type. We estimate the mass of this unseen object to be around 6.6 times that of the Sun. Given that it is obviously too much for a neutron star, the strange, invisible object is most likely a black hole. The gravity of its larger partner is stretching and twisting the orange dwarf, stripping it of its outer layers of star matter. Spiraling streams of flaming gas gradually approach the black hole, eventually forming a brilliant accretion disk. It was this brilliant disk that allowed for the discovery of the black hole. Around V616 Mon, there are at least a dozen stars, some of which most likely have their own planetary systems. One of these stars could potentially approach the black hole too closely and succumb to its immense gravity. In this scenario, the star will inevitably face the same fate as its current companion, the black hole. The mass ratio of a black hole primarily determines its interaction with other entities. The black hole's tidal forces have a greater effect on its companion the closer they are and the bigger the black hole is. They could distort the star, causing it to stretch in the direction of the system's shared mass center. Additionally, they have the ability to create pathways that bring star stuff closer to the black hole, enhancing its accretion disk. If the tidal forces are strong enough, they could destroy the object by turning it into a flaming ring. It is believed that planets might circle black holes in the same manner as stars do. Contrary to popular belief, black holes cannot indiscriminately absorb everything in their vicinity. Astronomically speaking, from the perspective of gravitation, they act exactly like any other star of the same mass. Therefore, despite how unbelievable it may seem, a stable planetary system may exist inside a black hole. Such systems can form in a variety of ways. First, a gas and dust nebula created following a supernova could be the source of new celestial objects. They initially create material clumps due to gravitational pull, which clash and draw cosmic dust. As a result, they eventually become planets and satellites, along with a significant number of other tiny celestial objects like comets and asteroids. It's possible that the accretion disk's radiation can warm them to the point where ice melts on their surfaces. That kind of planetary system might, in theory, be conducive enough for life to begin and, hopefully, evolve. Secondly, certain objects in a black hole may establish stable orbits around their new host after it devours another planetary system. Naturally, this transformation would result in significant surface alterations for the heavenly objects. As a result, a gas giant may lose nearly all of its hydrogen and change into a Chthonian planet, whereas an ice giant may change into an ocean planet. Thirdly, the gravitational pull of the huge object may also trap space rovers such as interstellar asteroids or rogue planets. Although we haven't discovered such a system in practice yet, it doesn't rule out its existence. However, if a planet is located too close to the center of the system and the black hole is large enough, other elements come into play. The celestial object will lose its atmosphere as a scorching hot stream of material creates the accretion disk. This material's friction will slow it down and draw it closer to the black hole. Extremely strong tidal forces will eventually tear the planet to pieces. The disk of accretion will draw in the debris, which will then gradually melt in the surrounding hot gas. The black hole will eventually engulf them and effectively integrate them into it. The primary distinction between the three primary categories of black holes in the cosmos is their mass. The majority of spiral galaxies have one of the first types in their cores. These massive black holes can weigh up to several billion solar masses. A galaxy's core typically has an incredibly high matter density, which is why a huge proportion of enormous, luminous stars are born there. Extremely densely packed, they quickly burn out and become black holes, which then quickly expand and frequently combine with one another. Consequently, gigantic objects form, encircled by vast accretion disks composed of extremely hot material. They shine so brightly in space that we can see them from billions of light years away, despite our inability to observe their galaxy. We refer to these objects as quasars. The second type of black holes is far more common than the first. They originate near the end of the massive star's life cycle, and their masses are similar to those of stars. These objects eventually enlarge and become intermediate mass black holes as they consume interstellar gas and other celestial bodies. Additionally, they have the ability to merge, producing gravitational waves that warp space over several light years. The theorized primordial black holes belong to the third category. Current theories about the cosmos genesis and evolution suggest their existence. It is possible that black holes with infinitely small sizes originated because of fluctuations in stuff that occupied space during the early stages of their growth. Estimates suggest that the smaller an item is, the faster it evaporates, and at the end of its life cycle, it transforms into an extremely strong electromagnetic impulse. According to modeling, primordial black holes with masses of approximately 1012 kilograms should be flaring up right now. However, no such event has been observed. A specific theory states that when extra high-energy elementary particles collide, a miniature black hole may arise. We call this type of black hole a quantum one. However, the conditions required for such an event to occur are unreproducible in laboratory settings, and the predicted life expectancy of these hypothetical things is so little that it is rarely detectable even with the most sophisticated and recent tools available today. Currently, we only recognize the existence of quantum black holes in theory. Naturally, it is very challenging to find such small, black items. Some of them also have a star partner, whose unusual movement pattern provides unmistakable clues about the presence of an invisible object nearby. Observing accretion disks is another widely used detection technique. We can distinguish these objects from other space-based light sources thanks to certain characteristic aspects of their spectra. Occasionally, we manage to photograph a disk containing a black spot, revealing the highly peculiar structure of the object under study. We can also discover black holes using the gravitational microlensing phenomenon. This entails tracking the enormous, invisible object as it moves from Earth to a far-off star. This modifies the star's spectrum in a unique way, but we must acknowledge that the success of this strategy depends on a number of uncommon circumstances. There is almost no question that space is full of numerous, dim, and difficult-to-see objects. One of them could be roving black holes. These enigmatic objects, cruising across interstellar space and soaking up all the light they encounter, are unlikely to ever divulge their secrets to us. Thanks for watching, and see you next time.